So this lemma is actually very useful, but we might wonder what happens if the obstacles in our picture, in our input, are not convex. So imagine that you have an obstacle like this and you still want to solve the robot motion planning problem. What do you do then? Well, what we can do here is that we can triangulate this convex object and we can look at it as a collection of triangles. For Minkowski sum, it still holds that you can write this equality. In other words, if you want to Minkowski sum the union of two regions, that's equivalent to the Minkowski sum each one of them and then uniting them together. This follows by just basic property of Minkowski sum, which is defined as one element from here plus one element from here. And you can open it up and you can see that that easily equals to first add one element from R, one element from P, and then union them because when you add R to an element from this side, then the element either comes from P or Q. If it comes from P, it's included here. If it comes from Q, it's included here. So this, you can show that this is an easy identity. Yeah. So by this identity, we could say that the Minkowski sum of this red polygon plus this blue polygon can be written as the union of the Minkowski sum of this red polygon with each one of those triangles. Since a triangle is a convex object, it follows that we can get that this union is equivalent to the union of a bunch of pseudodisks. Okay, so we are almost now done. This follows that, so this proves that the Minkowski sum, the complexity of P Minkowski sum with R is at most n times m. Which is actually tight. And one example is a shape like this. If you take a circle or any kind of round polygon and Minkowski sum it with this very rough looking polygon, then what happens here is that you get essentially don't have a picture here, but you get essentially the shape of this robot over here. That's how the Minkowski sum would look like. And if this one has complexity m, you get complexity m inside each one of these tooths of this cum, basically. So the total complexity of Minkowski sum will be n times m. And this is optimal based on this observation that we had. Oh wait, that's something I forgot to mention. I forgot to give a bit more details on why the complexity of P Minkowski sum R is n times m. This is because, if I go back here, from here, the blue one is the equivalent to the union of n triangles. Okay. Each triangle is a convex object, so when you say that union of triangles, Minkowski sum with R, based on this equality, this is equivalent to the union of each triangle Minkowski sum with R. This is a pseudodisk, and this has complexity m. This is because triangle has constant complexity and R has m complexity. And how many of them I have? So I have n pseudodisks with each with complexity m. So therefore, the total complexity is going to be O of n times m, based on what we have proved earlier.